Hey everyone, welcome to another video on time series and forecasting. In the previous video, I have introduced you with the exponential smoothing model, the simple exponential smoothing model. And in this video, I will show you how to fit a simple exponential smoothing model using R programming language. This web page contains the data on total annual rainfall in inches for London from 1813 to 1912. We will use the scan function to read this data just like we did before. We will set skip as equal to 1 to skip this first line. Now let us use the TS function to convert this vector rain to a TS object. We set the frequency as equal to 12 and start equals to C 1983,1 to tell the computer that this is a monthly data that starts from 1983 from the month of January. There is a separate video in this series where I have specifically discussed how to read time series data in R. If you haven't checked the video, you can check it out from the link given in the description box. Now when we pass this rain.ts object through the plot function, this will plot the series. From this plot, we can clearly see that this series is pretty random. This series has no trend and no seasonality. It seems like a simple exponential smoothing model can be appropriate for forecasting the values of the time series. Now let us see how can we fit a simple exponential smoothing model to this data for a small value of alpha. To fit a simple exponential smoothing model, we use a function called halt winters and put this TS object inside it. This function has three smoothing parameters: alpha, beta, and gamma. For a simple exponential smoothing model, we only use the parameter alpha and set beta and gamma parameters as false. Here you may have a question that why do we call this function halt winters when we are fitting the Brown's exponential smoothing model? And what are the functions of these parameters beta and gamma? Well, don't worry. I will reveal them shortly in my subsequent videos. For now, you can think of this function as the generalized version of the exponential smoothing models. So this program fits a simple exponential smoothing model to this rainfall data by setting alpha as equal to 0.2. We will call the object storing this model as rain_model. Now if you pass this model through the plot function, then this will give you a plot of the fitted model indicated by this red line here. This rain_model object has got an attribute called SSE, or the sum of squared error. This gives us the sum of squares of the difference between the actual and the fitted values. Like for all models, we want this value to be low. Now let us see what happens when we fit an exponential smoothing model with a high value of alpha, say 0.8. We will use the same halt winters function, set the value of alpha as 0.8 and set beta and gamma as false. Now let us look at the fit of this model. And here let me ask you a question. Do you think this model fits the data better compared to what the previous model did? Well, think about it. Of course, one way to verify this is to check the SSE value of this model. And here's what we see. The SSE in this case comes out to be 3105.4, which is much larger than the previous SSE of 1972.2, which means in reality, the previous model fits the data much better. However, if you look at these two graphs closely, then at the very first glance, apparently, it may look like the model at the top fits the data much better than the model at the bottom. But the SSE of the first model is much higher than the SSE of the second model in this plot. The reason why the first model apparently looks like a better fit is because its shape nearly matches the shape of the series. The second model, on the other hand, looks much smoother than what the original series looks like. But if you take a detailed view at the first model, then you will be able to see that the errors made by this model at different time points are quite large. But the errors made by the second model is not as much. This practical example clearly shows you that different values of alpha will lead to different kinds of fit. But our objective is to find that value of alpha that fits the data the best. In the next video, I will show you how to choose that optimal value of alpha using our programming language. And if you haven't subscribed to the video yet, what are you waiting for? We're going to have a lot of fun with numbers and data on this channel.